Welcome back to Year 11 Chemistry. So now we're going to be talking about alkenes. So alkenes are defined as a family of hydrocarbons that have a double bond between carbons as a functional group. So because they're very similar to our alkane family, except because they have this double bond within their structure, they have a new general formula. We can see why that's so, because we have two carbons that have a double bond between them. So bonds that would have been given up for hydrogens now are involved in this double bond. So we have a different general formula. So an example of an alkene here is our 4 carbon species with the double bond between the first 2 carbons that we see. Even though with our general formula this is based on a single double bond in the structure, if a molecule has multiple double bonds between carbons, then it is still classed as an alkene. It will affect our general formula, however. So our naming of alkenes is very similar to our alkanes. We have a prefix that tells us how many carbons are involved in the structure, and we then have the second half of the name coming from the family. So we have a different family now. So alkanes came from an alkane with a A-N-E on the end of the name. Now we're talking about alkenes with E-N-E on the end of the name. So the first compound that we have on the right is called propene, because we have prop, 3 carbons in the structure, and we have a double bond in the structure as well, so it will be the ene family. The second molecule has 4 carbons in the structure, so it is called bute, with also a double bond in the structure, so it is butene. But what happens when we shift the double bond along the molecule? So it's not just between the first and the second carbon, it's between, for example, the second and the third. Is this still butene, or is there another name for this compound? So these butenes are what we call isomers. So they have the same chemical formula. So basically they have the same number of each type of atom in the formula, in the structure, but their arrangement of bonds is different. So another way of saying that is they have different structural formulas. So we can see that because the double bond here is shifted to the middle of the molecule, and we have more hydrogens on the left-hand side of this molecule for the second one. So we're going to come up with some new rules describing the position of functional groups along a carbon chain for our organic molecules. So we place the lowest possible number that we can to a functional group right alongside our family name. So we do this in order for us to locate the position of a functional group. So we have the butenes from before, so we have our double bond between the first and second carbon in the structure for the first molecule. So because this is in the first possible location, we would assign this the name but1ene. So because we have the double bond in the first possible location, we assign it the number 1, and we have that between the number of carbons in the name and the family. So it's right next to the functional group name. With the second butene, because it's in the second possible position in the molecule, we then call it but2ene. So you can see that the number changes. The question then becomes, what do we call this third molecule? The double bond is shifted to the last possible position, so the third position. But we need a molecule that has a fully non-identical structure to another butene. So it needs to be completely different from these other molecules. In saying that, we can't just rotate the molecule in order to make it look like the other butene, because these molecules actually vibrate and rotate freely in space or in liquid or wherever they are. So they need to be completely different molecules, a different arrangement of bonds to be a different compound. So this molecule would be named but1ene as well. So have a go at naming these molecules now. Pause the video. If needed, go back and re-watch, but have a go now. Okay, so we see that we have 1, 2, 3, 4, 5 carbons in this molecule. So we're looking for a pent type molecule. It belongs to the ene family because it has a double bond in the structure, and it's in the second possible location from the left. So we see that we have pent-2-ene. But what about this structure, the second structure? We have a double bond between the second and third carbons, and there's 3 in total. So it might be a suggestion that we have prop-2-ene, but what happens is basically if we flip this molecule, we will achieve a normal propene, so with a double bond between the first and the second carbons. So what we've seen here is that basically if a molecule, if we change the double bond in the molecule, but it effectively doesn't give us a brand new molecule with different arrangement of structure, then we don't actually have to number that molecule. So we can just write propene, because there's only one way, possible way of making this structure with a single double bond between carbons. So there's no need to write the number next to the functional group. So alkenes have very similar physical properties to alkanes. So please go back and watch the alkane video discussing the physical properties of alkanes. All of those properties can be attributed to alkene as well. Okay, so alkenes, they contain a reactive functional group. So the double bond is actually the reactive site along this molecule. They also are combustible, just like our alkanes, but they have a higher carbon to hydrogen ratio, so they often give incomplete combustion. So we can see that we have complete combustion of this butene molecule, so C4, bute, and it's got the general formula of the alkene, so butene reacts with oxygen to give carbon dioxide and water, so our classic combustion reaction. But there are circumstances where we can get incomplete combustion with our hydrocarbons. So these equations here, with a change of carbon dioxide to carbon monoxide and also carbon, give us incomplete combustion. So when a situation arises where we have a incomplete combustion, or we have a situation we might suspect a incomplete combustion, evidence of that is actually where we have soot or just carbon in our products. So a way of identifying an incomplete combustion can be a black, smoky, sooty flame. So a classic example is if you go along a highway, you can see trucks that change gears, and they often have an exhaust pipe poking up near the cabin, up the top of the vehicle. And when they change gears, you'll see a puff of black smoke. That black smoke is due to a sudden stop in the engine's power output when they change gears. And basically in that moment, they achieve incomplete combustion in their fuel. So these reactions can be found in everyday situations as well. So alkenes also have an addition reaction that occurs. So the diatomic molecules such as bromine and hydrogen, dihydrogen, can be added to the double bond. So it's just a play on words with addition reaction stemming from bromine and hydrogen adding to the structure of the double bond containing molecule. So let's have a look at an example. So we've got bromine, so 2 bromines, they belong in group 7, so they just have a single bond between them. They react at the site of the double bond. So each carbon that was contained in the double bond then reacts to have a single bromine attached, single bond to that carbon. So each bromine has been added, so a single bromine has been added to each carbon that was in the structure. So basically we can use bromine to identify whether a molecule or a mixture contains double bonds. For example, our alkenes are usually colourless, but a bromine solution is orange. And when they are added to the structure of the alkene, they become colourless. So the mixture becomes colourless when a double bond is contained in the structure. So I've found a nice diagram here with alkane. So if bromine was added to an alkane that lacked a double bond, the solution would stay orange upon addition of bromine. But if the structure of the liquid contained a double bond, then the solution would react, or mixtures would react, and the orange solution would be taken up into the structure of the alkene, and the colour would fade to a colourless solution. So very similar chemistry now. We're going to look at the addition of hydrogen. So it works in the exact same way. So one hydrogen from each of the H2 reacts and gets added to one site on each carbon. Some terminology here is that we have an unsaturated alkene because there is not the most possible amount of hydrogen on the alkene structure, but once the alkene has reacted with hydrogen, so the word for that is hydrogenated, it forms a saturated alkane because it is saturated with hydrogen. It has the most possible hydrogen in its structure. So that's it for our alkenes. Thank you for listening. Don't forget to like and subscribe. I'll continue putting out more and more videos, not just year 11 chemistry, but all different year levels and also for mathematics. Cool. Thanks for listening.